So in this video, I'm going to be solving a few select problems from the Chapter 9 review. Don't be afraid to skip ahead using the timestamps in the video if you just want to skip to a certain question. I'm just going to begin with this first one where we're asked to graph this function x squared plus 2x minus 8. First thing we're asked for a few different things on this question, is the axis of symmetry, which a lot of times, again, I would label in my notes just like AOS. So the formula we know for axis of symmetry is this formula, x equals negative b over 2a. And if I substitute the pieces from my function, I can find out where my line of symmetry is going to go through that graph. So from this equation, again, if I have this form in standard form, ax squared plus bx plus c, I can just plug in the parts that I need for my axis of symmetry. So it looks like b is going to be the 2 value, and a is going to be just 1 because I just have x squared by itself. So if I simplify this, negative 2 over 2, I know that my axis of symmetry is going to be the line that goes through x equals negative 1. And on my graph, I just have to remember for my symmetry, for a parabola, it's pretty much always going to be the same. It's going to be a vertical line, and that x equals negative 1 line is going to go about right here. And this is technically not part of our parabola, it's just what we're going to use later to graph it. Then to find the vertex, what I need to do is I need to take that value from my axis of symmetry and go ahead and plug it back into my function. So if I plug that in, again, my function x squared, so negative 1 squared plus 2 times negative 1 minus 8, I want to figure out what the y value is going to end up being here. So it looks like it's going to be 1 minus 2 minus 8, which I think comes out to negative 9. So I know my vertex is going to be on the axis of symmetry that keeps the x value the same. When I plugged in that x value, I got negative 9 as a y value, and that looks like it's going to be right here on my graph. So I know that this is what I can use when I'm starting to graph the parabola. I need to use then the y-intercept for the next part of this graph. Y-intercept, we don't have to do a whole lot of work. We just have to know y-intercept is the constant at the very end of that function. So if the y-intercept is negative 8, we're also asked as part of our graph to find a total of 5 points. So let's just label what we have so far. We have the vertex at negative 1, negative 9. When we saw the y-intercept, that was at 0 and negative 8. And if I want to get another point, I can use my symmetry to reflect over that axis of symmetry and get a third point, and this would be negative 2, negative 8. Again, we're just using that y-intercept, flipping that over the line and seeing where another point would go. So if I need a total of 5 points graph, that means I just got to find one other point and then use a reflection. So let's say if I haven't found a x value for positive 1 yet, I can plug that into the function. So positive 1 squared plus 2 times positive 1 minus 8. I just want to see what the y value ends up being. 1 plus 2 minus 8, I think, is going to be negative 5. So if I find another point when I plugged in 1 and I got negative 5, if I want a total of 5 points, we're at 4 so far, I can use another reflection and come up with this point right here. That looks like that's going to be negative 3, negative 5. So I have 5 points labeled. I can just draw my parabola as best I can through those. And last thing we're missing here, sorry, I forgot to label the y-intercept. That we knew is at 0, negative 8. We have our 5 points, but actually what I could have used instead of 2 other points, it also asked us for the solution. So it doesn't say at the very top of this, but it says state the solutions based on our graph. So solutions based on our graph, we could have factored this and find the solutions that way. But if our parabola is accurate, it looks like it's going to head through about right here. And if it was perfectly accurate, I think that would be right at the point at 2. And the parabola also crosses through the x-axis here at negative 4. So we know the solutions to our function are positive 2 and negative 4. So those would be the solutions based on our graph, again, just based on where they cross the x-axis. And remember, if you would have factored this, so if I factor x squared plus 2x minus 8, we're going to be doing this again a little bit later. I could factor that as x plus 4 and x minus 2. So if I know that I'm trying to find a point where those reach 0, negative 4 and positive 2 would have been our solutions. And again, that's what I have listed over to the side. You know what, just to keep this consistent, I'm just going to label those as points. So the point 2, 0 is where it crosses the x-axis on this side. And looks like 0, or sorry, not 0, that's negative 4, 0. That's where it crosses on the other side. So those are the two solutions to my equation. So that was our graphing example. Next example we have is from number 3. I'm skipping number 2 because it's a similar question. You can see my work off to the side. I'm doing number 3. It's a little bit more complex example, and this is what we call completing the square. So completing the square, first thing I need is actually just the first 2 terms. And if I'm trying to find the term that completes the square, the thing I have to do in number 3 that I didn't have to do on number 2 is just divide out a GCF to simplify this. If I divide everything by 2, it's going to make our question a lot easier. X squared plus 4x equals negative 2 is now what I have to start the question with, basically. So if I want to find the term that completes the square, that's following the formula b over 2 squared, where b is just the coefficient of my x term. So if I plug in 4 over 2 squared, I want to simplify it. 2 squared would come out to be a positive 4. So that's already actually our first answer. The term that completes the square would just be adding 4 to both sides. So then to actually find the solution, again, using our completing the square method, I take that term that we just found from the first part of our question, and we're going to take it and add it to both sides of that equation. Again, I simplified the equation first, but using that simplified equation, adding 4 to both sides is just taking our answer from the first section and adding that to the left and to the right. Because what that does is it completes a perfect square trinomial on the left-hand side. Remember, you don't really have to worry about the factoring. It's always just going to be that half of the middle term. And on the right-hand side, it just comes out to positive 2. So if I then take a square root, I have x plus 2. I got rid of that second power. Plus or minus, we have to remember for the square root of 2. And last step is I just got to subtract 2 from both sides. So it looks like for my final answer, and we could leave it in this form, I just have negative 2 plus or minus that square root of 2 on the right-hand side. And again, that was completing the square method. So now we've done completing the square and graphing. So next question, it's asking us to solve by using the quadratic formula. And this is always handy to write at the top of any homework or any test that you have, just to remind yourselves of that actual quadratic formula. We're taking a, b, and c from our function and substituting it into this sort of big equation. Nice thing is that it works on every question. Not nice thing is that it's kind of a lot of work to simplify. So if I'm just taking the pieces from this equation, first thing I actually have to do on number 4 that I didn't have to do on number 5 is get it into standard form first by subtracting 3 and getting that right-hand side equal to 0. Now I can plug the pieces in for my quadratic formula. Negative b is negative 5 plus or minus square root b squared minus 4 times a times c. And that's all over again 2a still from my function. So most of our work again is just simplifying. So positive 5 now plus or minus 5 squared would make 25. So yeah, just actually to stop, I say this is like negative 8. I'm kind of doing multiplication in my head one step earlier. So negative 8 times negative 3, if we want to do this in our heads a little bit better, is coming out to 24. So that's how I'm thinking about this when I'm multiplying, trying to do that in my head without a calculator. So now that I have this a little bit more simplified, this, it looks like, is going to come out to a nice solution because I have 49 inside of a square root. 49 we know is a perfect square. So if I write this as 5 plus or minus 7 over 4, last step is we have to remember plus or minus means 2 different operations. 5 plus 7 would make 12, and 5 minus 7 would make negative 2. And if I take one more step to simplify, I get the answers 3 and negative 1/2. So 3 and negative 1/2 would be our answers using, again, that not completing the square, using our quadratic formula. And I know that when I actually don't have a radical answer, if I just have something like 3 and then a fraction, I could have used factoring. We're not told to use factoring, we're told to use quadratic formula, but if I have a question that comes up that I do need to use quadratic formula, we're going to see an answer like this that uses a radical. So next example we're going to show is using the discriminant. And discriminant just means that piece inside your square root from quadratic formula. That's only looking at b squared minus 4ac. So just like our last question, we have to make sure this starts off in standard form. One step at the very beginning is to add 5 on both sides here. And then if we want to find the value of that discriminant, again, I'm just plugging in those pieces just into that one part of that quadratic formula. So b squared minus 4 times a times c. We just want to simplify, so 36. And again, I'd look at this as negative 8 times 5, so that's 36, looks like minus 40. So negative 4 is the value of our discriminant. We don't have to do the entire quadratic formula, just that part that would go inside the square root. And since this is negative, we actually see this come up later in this review as well, if you guys have solved the whole thing. Negative inside the square root from the quadratic formula means that we're going to have 0 solutions. So you could just say 0 for the second part of this, or something like 0 solutions. Doesn't really matter how we write it. But again, that's like if I plugged in a negative value into my square root. We know we can't take the square root of a negative, so that's why any negative value for the discriminant is going to have no solutions. So in this next section, notice it says solve using any method. I'm going to choose certain methods on each one that I think are pretty good to apply. But again, it kind of just matters what you're comfortable with. And notice I've left some of these blank that we're going to solve in this video. Other examples you guys can find from that practice solutions. So first method that I chose, and notice I kind of labeled this as factoring ax squared. This actually comes all the way back to chapter 8. You could just look at this and use quadratic formula right away if you're comfortable with simplifying that. But I think on this question, if I use my method where I multiply 6 times negative 1, that means we're looking for factors that multiply get negative 6 and add to get 1. That's the coefficient of your x term. And this, I think, does work with factoring. If I use 3 times negative 2, it multiplies to get negative 6, and it also adds to get 1. But this is where we actually have to remember, if I have that leading coefficient as a 6, I'm not done just by using the 3 and the negative 2. This is where I have to factor using what we called the Xbox method from chapter 8. So plugging those pieces into my box, again, we already have the first term and the last term done for us. We used our factoring to figure out how to break apart that middle term. And now, if we can remember, we're just trying to factor out our greatest common factors. In the first column, I can factor out 3x, and in the second column, I can only factor out a negative 1. And then if I move down to the first row, I can factor out 2x from both of those, and I can only factor out a positive 1 from the second row. So this is how this function factors 3x minus 1 and 2x plus 1. Since we're still trying to find solutions where they're equal to 0, we're using what we call the zero product property. Either the first part of that question is going to be equal to 0, or the second part could be 0. That would make the entire product 0. So if I just solve each equation that I made, 3x equals 1 if I add, and x would be 1 over 3 if I divide. Doing the similar steps on the other one, if I subtract 1, I get negative 1. If I divide, I get negative 1/2. These are going to be our two possible solutions. Again, it doesn't really matter how you label your answer. You could use the word or, but a lot of times I'm just going to write both of those. We know I could use the value 1/3, or I could use the value negative 1/2. Also, it doesn't matter which order you put those answers in. So that was our example using factoring with a leading coefficient that's not equal to 1. So the next example I chose is factoring when I actually only have 2 terms. So a lot of people, I think, make this kind of question harder than it should be. If I notice that they both have a GCF, I could take 3x and divide both of those by 3x. So let me show that work as division. I could divide the greatest common factor out from both of those, and that's the only step I would need to actually factor this one. If I factor out the greatest common factor, I get something that looks like this. And this is actually right where we were right here. We just have 2 things multiplied, and we know they're equal to 0. So we're doing a similar approach. We know either the first part of that's going to be 0, or the second part of my question is going to be 0. And just like we did on the last question, 0 divided by 3 is just 0. And if I add 3 and then divide by 2, if I divide by 2, I get my second solution. So just like our last answer, 0 could be one solution, and 3 over 2 would also work. Doesn't matter which order you put those in. So I skipped over number 9. So number 9, if you're looking at my work, I believe what I used is that quadratic formula because I don't think that one was factorable. And at first glance, number 10 looks like one we might have to use quadratic formula too because those look intimidating in terms of your factoring. But if I remember this, again, back from chapter 8, if my first term is a perfect square and my last term is a perfect square, I could check to see if they follow a shortcut first. And I think this one will. Take a square root of that first term, I get 5x. Take a square root of that last term, I just get 6. And if I multiply those, 2 times 5x times 6, I get, I think, 60x, which matches our term in the middle. So if we can remember all the way back to chapter 8, this means this actually follows a perfect square trinomial of the form first term plus the second term and just raise to the second power. So if I use that as my factoring, 5x plus 6 squared equal to 0. You could always double check this. If I multiplied this out, I should get back to that original trinomial. That just means I have to take this solution, kind of like what we did last time. And notice that we only have one term that's raised to the second power. If I want to get rid of that second power, I can take a square root. Now I just get 5x plus 6. But square root of 0 is just going to be 0 by itself. I don't need any plus or minus. So this is a kind of a rare example where we're only going to have one solution. If I keep solving this one equation, I get 5x equals negative 6, and x would end up being negative 6 over 5. So could happen, again, if I have a perfect square trinomial where there's only one solution to my question, and that would be that fraction that we found. So skipping a bunch now, because these are just really repetitions of methods that we've used before. On number 11, I'm using the same kind of question, same type of solution as number 10. Number 12, it looks like I'm using completing the square. Number 13, I also use completing the square. And 14 and 15 are both using the method that I'm going to apply here on number 16. And that's using square roots. If I don't see any x term, like on number 13, I have like a negative 8x. I don't see any x term on 14, 15, and 16. All I see is an x squared term and in constants. What I can use is just square rooting. I don't have to do any kind of factoring. But the first thing I have to do is make sure the x term is isolated still. So if I want to get x squared by itself, on this question I'm going to get negative 49. And I chose this specific example to work over because if I then try to take a square root, I get x on the left-hand side, but square root of negative 49 is not going to work on the right-hand side. So we can just say for this sort of question, no solution, and move on. I know I can't take the square root of a negative and get a real number answer, so since that's not going to work, I can just leave it at that. I know I can't take the square root of a negative. If you want to see the complete solution, like on number 14, take the square root of 64, I get plus or minus 8, so I use that for my answer. Take the square root of a fraction, I can still get an answer. If I take the square root of a negative, I'm just not going to get a solution. So last one that we're going to cover is factoring. Actually a little bit easier example of factoring, where I just have x squared, I don't have a leading coefficient. I use the same method on number 17, and actually 17 maybe would have been a better one to show because it has an extra step in front where I have to get them all on the same side. This one we already started in standard form, so I think this one is factorable if I think of numbers that multiply to get negative 36 and then add to get 5. Again, this is still work from chapter 8. I think the numbers 9 and negative 4 would work for that. So if I factor this expression is x plus 9 and x minus 4, we still know it's equal to 0, so we're going back to our zero product property. X plus 9 is equal to 0, or x minus 4 is equal to 0, and pretty quick solution for both of those. I get either a negative 9 or a 4, which again are both solutions. So I can just list that as negative 9, or sorry, not positive 4, that would be a negative. Those would both be solutions to my function. Just to finish and pointing out like number 19, I use quadratic formula. I don't know if that's factorable, I don't think it is. And actually we see something similar. If I take the square root of a negative, it's not going to work. And on number 20, if we're trying to solve that one, I could again use quadratic formula, but I think that one's factorable. If I use that factoring method with the first term not equal to 1, we can factor that using Xbox and then find our solutions using zero product property.